we started to talk about some revision of some concepts of probability and statistics. And then we start to define a little bit about the probability, the things that you knew. And we define what is a mutually exclusive, how we can use it in order to calculate the probability. And now let's continue by still defining some things that you knew from before, but it is important to revise it. So again, another definition. Some of these definitions are actually theory, and but you don't need to know the proofs. If A1 till AN are mutually a sequence of mutually exclusive events. What does it mean, mutually exclusive? Yeah, mutually exclusive means that A1 intersected by A2 intersected by AN is equal to empty. Then the probability of A1 union AN is equal to the probability of A1 plus the probability of A2 plus the probability of AN. Now, let's do an example, but this example is a special example because we won't have any numerical numbers in here, but we want to get some conclusions. If I write here, you can see, right? So, assume given the following Venn diagram, it is S. This is the sample space that we have. And this is A. Can you tell me that what is the shaded part? A prime, complement of A. Now, we know a few things. What is A intersected by A prime? Null, because there is no intersection. What is A union by A prime? It's S, the whole sample space. So we get the probability of A union A prime is equal to 1 because this is the probability of S. And the probability of A intersected by A prime is equal to 0, which is the probability of null. You may remember something which is known as the Morgan's law. Which is A union B prime and A intersected B prime. Do you remember that? What is this? This is A prime. Union prime is intersection B prime. And here A prime, the intersection prime is union B prime. We may recall that A prime is equal to A. So these are some useful things that we need to know. If A, B, and C are events in S, then probability of A union B union C is equal to, what's that? Do you remember? This is also something that we might know it from undergraduate or high school level. Here we have a Venn diagram like this. In general, A, B, C. This is definitely has the PA plus PB plus PC, right?
Yeah. Minus A intersection.
We know that there are some elements in here. So I have to and it will be counted twice, so I have to remove it once. So it is minus probability of A intersected by B, right? Minus, there might be some elements in here, probability of B intersected by C minus the probability of A intersected by C, because there can be some elements in here. However, we know that there can be an element in here which is inside here, which is inside here, which is inside here, which we have removed them. Now, let's see what happens. We have included it like twice, we remove it 3 times, so we have to bring it back, right? So we are adding it P, A, intersected by B, intersected by C. Okay? Now, knowing that we have the mutually exclusive events, and knowing that when we are mutually exclusive, it means that there is no intersection, and knowing what is a complement of a set, we can have now a new definition. And this is a definition for partition. A collection of events, let's say A1 till AN, are called partition of the sample space S if 1. A1, A2 till AN are mutually exclusive to A1 union till AN is equal to S. So if we have these two conditions for our events, then we call them, they are partitioning S. What it means is that is this from Venn diagram point of view. This is S, and partitioning means this. Let's say A1, A2, A3, A4, here we have 8 partitions. There is nothing common between these events. They are mutually exclusive. And when I put all the events together, I will get all S. What we had in the previous definition, let's say we have A, we have B, and let's say we have C. Here A, B, and C are mutually exclusive because they don't have anything in common. But they are not partitioned because, let's say that there is an element X which is inside S and it is not inside all of them. In other words, if I put A, B, and C together, I cannot get S back. So this is a definition of a partition, and this is what we have when we have a mutual exclusive event. So we have a corollary which we get hence if A1 till AN are partitions of sample space S, then the probability of union of I from 1 till N. Look, this means A1 union A2 till AN is equal to, we know that when they are mutually exclusive, the probability of union of all is the addition of all the probabilities. So now they are partitions. What is this? It's 1. Because still it is the addition of all the probabilities, but I know that the addition of all the probabilities in case of partition will give me the S, which is the probability of 1. Now, finding a partition is sometimes very useful, but can you please tell me how I can easily find or I can easily divide my sample space into partition? What is the first trivial solution that comes into your mind? Any event, let's say A, and its complement, A prime, for a partition for sample space S, which means that if I have A and I have A prime, they are mutually exclusive and their union is always S. So it means that any event and its complements are dividing in the sample space that we have into different partitions. Now, we have a very famous theorem known as law of total probabilities. And it says, for any partition, for any sequence of partitions, or for any set of partitions, A1 till AN. In other words, I have sample space S, and I have divided it into n partition. Then the probability of an event B is equal to the probability of B intersected by A1 plus the probability of B intersected by A2 plus the probability of B intersected by AN. This can be written, and the proof is what I write in blue. This can be written as probability of B intersected by A1 union A2 union AN. Well, what is A1 union till AN? It's sample space. Why? Because there are partitions, right? So this is S. So I have probability of B intersected by S. Any set intersected by S is that set itself. So it is equal to the probability of B, right? Because the intersection of A and the whole thing is A. So probably the intersection of any set with the big set is that set itself. What is the union of any set with S? Is S, because S has everything inside. Now, let's do an example. I am sure that all of you have seen the card decks, the cards that we play, I don't know, blackjack, poker, whatever you want to play. A set of card deck can be divided into 3 partitions. A1, which is even number, A2, which is odd numbers, and A3, which is faces. Okay? So if I have the set of the cards, which are 52 cards, I can divide them, let's say, into A1, A2, A3. If a card that I pick is an even number, it cannot be a face, it cannot be an odd number. If it is an odd number, it cannot be a face, it cannot be an even number, and so on. So, we want to find the probability of picking a card. So we want to pick up a card, and we want to see that what is the probability of picking that card to be hard. We know we have 4 symbols, right? We have four symbols in a card, and they are heart, club, spade, and diamond, right? And each of them has 13 cards. And this means that, and they're all equal probable. So by looking at this, can you tell me that what is the probability of having heart?
13 over 51.
Yeah, 13 over 52, which is 1 over 4. Now, what we want to do we want to find the probability of heart by using the law of total probabilities. Now, this is a very simple example. Of course, the easiest way is to do this, but we know the answer. We want to confirm it if we get them the same thing. So, let's define what is B intersected by A1, what is B intersected by A2, what is B intersected by A3. All the hearts
from even numbers?
Yeah, hearts with even numbers. Hearts with odd numbers. Hearts with, let's go, faces. Now let's give them values. How many even numbers do we have? We have 2, 4, 6, 8, 10, right? 5. So 5 even number for each, multiplied by 4, so we have 20 even numbers. Then we have 3, 5, 7, 9. So we have 4 multiplied by 4, 16 odds, right? So we have 4, 5, 9, and we have 4 faces, so we have 16s also in here. And it's ace, jack, queen, and the king. So, hearts. How many elements do we have for intersection between being heart and being an even number?
5.
5. So, what is the probability of B A1? Over 4. Then the probability of B union A2. Over 16, 1 over 4. And the probability of something weird, A3 is 4 which is 1 over 4, right? Are we correct? Hearts will be odd. So, then the probability of B should be the probability of each of them to be added to 3 over 4. Something is here.
I think it's while counting the even numbers.
Sorry?
I think it's while counting the even and the odd numbers.
It's what?
While counting the even and odd numbers between 1 and 13.
Which one?
The first one you started.
Okay, even numbers are what?
Between 1 and 13.
2, 4, 6, 8, and 10. So there are 5 of them. So 5 for each of them. 5 multiplied by 4 is 20, isn't it?
How about 12?
12? We don't have 12. Have you seen cards?
Okay.
It's ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then we have jack, queen, and king. So these are the faces.
Okay.
So we have 4 faces in each set. So it means we have 16 here. We have 1, 2, 3, 4, 5 even numbers in each set. So 5 multiplied by 4, there are 20. So we have 20 in here. We have 16 in here. And we have 1, 2, 3, 4. 4 multiplied by 4, 16 in here. And the addition is 32 plus 20 is 52. And the B is this part. The B is this part. So what happens is that we should see what is this portion. This is not 1 divided by 4. This is 5 divided by 52. This is 4 divided by 52. This is 4 divided by 52. And if I add all of them, what I get is 9 plus 5 is what? 14 divided by 50.
9 plus.
No.
11. No, 8 plus 13. 13.
Should be.
It's too early in the morning, right? So it's 1 over 4. Why divided by 52? Because we have 52 samples in total. We have 52 in here. What is the probability of A1? 20 divided by 52. Okay? Because this is a law, it shouldn't fail. Okay. Now, there is, apart from this law, there is a very fundamental methodology which we can use in order to find the number of samples, like here, to have the number of samples inside an event. Of course, sometimes like this, it is easy. You can write it down to see how many samples you have. But sometimes it is not that much easy. And we are using a very important method which is called counting sample points. This is the title. And we are using a methodology which is called a tree diagram. A tree diagram is a useful visual tool to systematically list the elements of sample space and a very famous example is tossing a coin twice will have these sample points. We know that if I toss a coin twice, what are the sample points? Head, 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 and head, head. But with the tree, what we do is this. We start to toss a coin, and we know that we will get either a head or a tail. In here, I will toss it again, so I may get again a head or a tail. Or if I have a tail, I will do it and I will get a head or a tail. So what are the sample points? Head, 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 tail, tail, head, tail, tail. So this tree is actually very, very useful if we want to see how many sample points we have and like how many of them are satisfying the condition that we were looking for. Of course, for tossing a coin twice is a very simple example. It's a very simple example, and we already knew about that one before. But let's do a few more complicated examples, which we will see that the tree will help us quite a lot. What are the outcomes of tossing a coin followed by rolling a dice. So here what we do, we have a coin. So we get either head or tail. Now, imagine that we have got head. Now we go and roll them dice. And in order to do it, we know that with the dice, we are getting 6 outcomes, right? Or if we get a head, the tail, we will do it and we will get 6 outcomes. So what are the outcomes? The whole outcomes that we get is H1, H2, H3, H4, H5, H6, and then tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. Now, the tree actually helps us to develop a rule which is called a multiplication rule. And this multiplication rule is in this form. What's your name?
Raymond.
Raymond. Yeah, Raymond. Raymond has two, let's say, pants and 3 t-shirts. How many different ways can he wear? So Raymond has 2 pants, 2 trousers, and 3 shirts. So we want to see how many different ways he can wear the outfits that he has. So this is Raymond, and he can start with the trousers. So picking up the pant 1 and the pant 2, right? And if he picks the pants 1, the trousers 1, he has 3 choices of the, we call it t-shirts, right? 3 t-shirts. Let's say T1, T2, T3. So for the pants 2, if you choose the pants 2, he can have T1, T2, and again T3. So can you tell me that how many different forms he has? 6. 1, 2, 3, 4, 5, 6. Actually, this is resulting into these important rules. How many pants did we have? 2. How many shirts did we have? 3. 2 multiplied by 3, we have 6 different forms. How many different forms do we have in a coin? 2. In a die, 6. 2 multiplied by 6, we have 12. So these 3 will help us to develop something which is called a multiplication rule. This is the definition. If an operation can be performed in R1 ways, And if for each of these ways a second operation can be performed in R2 ways, then the two operations can be performed together in R1 multiplied by R2 ways. R1 multiplied by R2 ways. All these few examples that recently we have done are very good examples of this multiplication rule. Like tossing a coin twice. R1 is 2, R2 is 2, so all total weight is R1, R2, which is 2 multiplied by 2, which is 4. Example, tossing a coin followed by rolling a dice. R1 is 2, R2 is 6, total weights or total number of points or total number of outcomes is R1, R2, which is 2 multiplied by 6, which is 12. But one thing that we have to note in the multiplication rule is for each outcome we have the same behavior. In other words, we do not say that if Raymond choose pants 1, he has 3 shirts to choose, and if he has pants 2, he has, let's say, 5 shirts to choose. So it doesn't matter what you choose, the next one is independent from the first one. In that case, we can use the multiplication rule. Otherwise, we have to stick with the 3 that we have. 3 is very general. But here we have this very important notation. For each of the outcome in the first way, we have independent, similar way of treatment in the second one. So let's do another example, which you see that in here, we need to use only the 3 diagram. And the example is this. A coin is flipped and then flipped for the second time if a head occurred the first time, if a tail occurred on the first flip, a dice is rolled. So this time, as you can see, we have different ways. We don't have the similar approach of continuing, although the 2 different ways that we do afterwards are kind of irrelevant from each other. But we know that their appearance depends on the first one. So what we do is this. We start, we toss a coin, we get the head and tail. If it is head, we toss a coin again, so we get head or tail. If it is tail, we are rolling a die. And it is 1, 2, 3, 4, 5, 6. So what are the outcomes? The outcomes are HH, H tail, tail 1, tail 2, tail 3, tail 4, tail 5, tail 6. And how many outcomes do we have? 8 possible outcomes. So here, multiplication rules does not apply here. So this is an important note. Now, I write an example which I want you to do it at home to practice just a tree. It will be a very huge big tree. You do not need to submit it to me, it's just for your own practice. Let's call it a practice. Egils is building a computer from parts. Okay, Egils, which is sitting here, he is now building a computer. He can buy the motherboard. I use MB, which is motherboard, from 2 companies, namely A and B. So he's careful, so he doesn't go to the first shop to buy. He looks around and he sees that he can buy from 2 companies the motherboard that he is looking for. For the RAM, from 4 companies, namely A, C, D, E. The hard disk drive from 3 companies, let's say B, D, and F, and the graphic card from, again, 2 companies, let's say G and H. For each part, he can equally likely to buy any one of the companies manufacturing that part. In other words, he doesn't doesn't know the CEO of any of the companies, so say that one of them is his friend, so he favored that. All the companies are equal for him. So the question is this. What is the probability of the event, let's say X, that aliens build a computer that has at least one part from company D. So what you have to do, you have to make a huge tree so you can see how many samples you have. This will be the denominator for the calculation of probability. Then you will see those elements which has at least one D. And you will count how many of them you have, you put it on the numerator, and you get the results. And I don't know what is the result. We will get back to this tree and we will talk about it, that what will happen if the companies are not equally likely. Then we can still use the tree structure in order to calculate what is the total probability at the end. Another theorem. Before we go to another theorem, do you have any question? I mean, your silence is good because it shows that you understand everything. But I also understand that this is kind of a revision. With high probability, most of you have seen it before. Is there anyone who has never seen these things before? Good. So what is the result? I think the result is like 1/2. But the theorem, I'm not so sure. The theorem says if an experiment can result in any one of n different equally likely outcomes, and if exactly n of these outcomes correspond to an event, let's say A, then probability of A is equal to, what is the probability of A? Come on, you have seen it before, you said. So. We have sample space, which we have capital N number of elements. We have event A, which has lower n elements. What is the probability of A? It is lower n divided by capital N. Because this is the total number of A, that elements that we have in A, and this is the total numbers that we have in the sample space. The definition for generalized multiplication rule. Previously we wrote the definition for the multiplication rule for two elements, like two sets of scenarios. But we can actually have series of scenarios if they are all repeated one after each other in the equal form. If an operation can be performed in R1 ways, and if for each of these a second operation can be performed in R2 ways, and for each of the first two and third operation can be performed in R3 ways, and so on, then the sequence of operations can be performed in R1, R2, RK ways, if we have, let's say, k sets of operations. As an example, in the practice question, which is this one, we have for company 1, how many way of selections do I have? Sorry, for component 1. Okay, component 1. How many way of selections do I have? 2. It's either A or B. For the component 2, I have 4. For the component 3, I have 3. And for the component 4, I have 2. So the total number of outcomes will be R1, R2, R3, R4, which is 2 multiplied by 4 multiplied by 3 multiplied by 2, which is equal to 48. In other words, when you make a tree, you will see that at the end you will have 48 possibilities. Now, we know that it doesn't matter, let's say, which of the components 1 and 2 you have taken, still you have 3 choices for the component 3, right? So it doesn't depend that if you choose a component from a company, let's say B, for the component 2, then you have different type of alternative. We can expand our example with Rahman and say we can say that okay, he has 2 pants, 3 shirts, and let's say have 4 hats. So what is the combination of the ways that he can wear? So you have to multiply the 6 by 3 and say that 18 different ways. Now, I wanted to give you another question to solve for. Now, we want to talk about the permutation and combination, which again, you might know it from high school. Permutation is an arrangement of all or part of a set of objects here. Order matters. In other words, head and tail is different from tail and head. The number of permutation of n objects is, if I have n objects, how many different ways can I put them together? N factorial is n factorial. It's easy to see why it is n factorial. Do you know n factorial? Is there anyone who doesn't know what's factorial? Imagine we have n choices, 1, 2, 3, 4, till n. So at the beginning, how many choices do I have? N. Then how many choices do I have in here? N minus 1, n minus 2, n minus 3, till at then I have 1. And use the multiplication rule. So what I get is n multiplied by n minus 1 multiplied by n minus 2 multiplied by 2 multiplied by 1, which is the n factorial. Note, 1 factorial is 1, 0 factorial is 1. Another smaller note. Permutation are used when we are sampling without replacement. What it means is you have n choices, right? So you pick one, then because you have picked it, it means you are left with n minus 1. So we don't put it back. You have a box of, let's say, 20 numbers, and you want to see what are the combination of these numbers, which is 20 factorial, but it requires that when you pick up a number, you will not put it back, right? So now we talk about sampling without replacement, so we can now do two definitions on sampling without replacement and sampling with replacement. Sampling without replacement means after choosing an object, it is not put back into the set of possible choices for the next round. And we have the definition, which is sampling with replacement, which means after choosing an object, we put it back in the set of possible outcomes for the next round. So if we have the sampling with replacement, and if we have n objects, how many ways can we choose an object? The number of choosing an object is objects with replacement is now I have a location. How many choices do I have here? N. How many choices do I have here? N again. How many choices do I have here? N. So it will be n power n. Now, we have talked about the permutation, let's talk about combination. The number of possible combination of n discrete objects taken R at a time is, we show it as CNR, which is also defined as n combined R, which is n factorial divided by R factorial multiplied by n minus R factorial. And here we know that order does not matter. Order does not matter. NCR is also defined to can be calculated by NPR, which is number of permutation of R of N divided by R factorial. So this is number of permutations of R out of N objects, which is N factorial divided by N minus R factorial. Again here, we are sampling without replacement, right? We are sampling without replacement. So let me give you a practice question. These are very, very simple things, and as I said, you might have seen them even in high school. In this course, we want to talk about the random variables and random processes, then talk about the hidden Markov model. But you need to know this because in one small part of the question, you need to calculate the number of combinations. So we don't want to, at that point, find out that you don't remember all those combinations stuff. Now, practice. How many ways are there to put 5 x's and 4 o's on a tic-tac-toe board? And the board for a tic-tac-toe is something like this. So, hint, the answer is number of ways to put 5x multiplied by number of ways to put 4 o's. So you have to calculate how many ways you can put 5x, then you have to calculate how many ways you can put 4 o's, and then you will get the result, which answer is 136. Now, we will start the next lecture by talking about conditional probability. Still, I believe that conditional probability is something that I assume you knew it, but I'm still revising it. And after, when that one is finished, we will start to talk about what are the independent events and so on. Do you have any question? If you have no question, this is the end of the lecture for today.